Hey everyone, welcome back. We're going to start a new chapter today. So this is chapter 5, subgroups. And so we'll start with a definition. So let's let G be a group. Remember at this point and from here on out, we just say let G be a group. I don't need to say with operation star. It's understood that G has an operation, and we'll indicate that by juxtaposition. So a subset, capital H, of G is a subgroup of G if H is a group. All right, so if it's a group on its own, but we have to be a little bit careful if it's a group using the operation that it gets from G, so the same operation that we have in G. So it's a group under the operation inherited from G. Right? So when this occurs, we say that H is a subgroup. So we should be very careful here, right? So let's say it. So that's the end of the definition, but I just want to give this note, right? If G, and I'm going to use a symbol for the operation now. So if if G star is a group, right? So I want to say now we've got G with operation star is a group, then H is a subgroup of G. When you say these words right here, H is a subgroup of G, this means that H comma star is a group, right? So I want to just make sure that this is clear, that when we talk about this notion of subgroup, it's got to be with the underlying operation that G has. In other words, it's the operation that H inherits from G. In this case, so notation then, we write H, and then the symbol we use is a less than or equal to symbol, right? So when you see that less than or equal to symbol, you read this, H is a subgroup of G. So H is a subgroup of G. So let's look at some examples. So our first example, the group of integers, remember that's under the operation of addition, is a subgroup of the group of rationals. Anytime when we talk about the group of rationals, that is by default the operation is addition. And then the set of rationals, or the group of rationals, is actually a subgroup of the group of real numbers. Remember, the automatic underlying operation on the real numbers is addition, and the real numbers is a subgroup of the group of complex numbers. All of this is under addition. What else do we have here? Q star, now that is the group of non-zero rational numbers under the operation of multiplication. That is a subgroup of R star. And then another example, Z star is a subset of Q star, but Z star is not a subgroup of Q star. Why is that? Well, because Z star is not a group. Right? We showed that earlier. It doesn't have inverses. Some more examples. If G is any group, so if G is a group, then the set consisting of just the identity is always going to be a subgroup of G. Right? So let's see now. What does that mean? It means that first of all, it has to be a group, which means that it's closed under the operation. Well, E times E is equal to E, so that means that this subset right here is closed. Associativity, well, associativity holds in G, which means that it's going to hold when you multiply elements in this subset right here. What else? Yeah, it's got the identity, right, because the identity is in it. And so then the last axiom, inverses, well, E is its own inverse, right? So I just went through the axioms real quick and showed that this actually is a group under the operation for G. And one more, and G is a subgroup of G. Right, so anytime if you have a group that's not the identity itself, then it will always have two subgroups. Right, guaranteed to have these two subgroups. This one has a name, by the way. This is the trivial subgroup. All right, so the subgroup consisting of just the identity is often referred to as the trivial subgroup. A piece of terminology here. So if H is a subgroup of G and H is not equal to the trivial subgroup, so if it's some other subgroup of G, right, then, oh, no, that's not what I want to say. No, sorry. If H is a subgroup of G and H is not equal to G, that's the case I want to focus on. So if H is a subgroup and it's not all of G itself, then H is a proper subgroup. So now an example, or another example. So let's look at the group of integers mod 6. So Z6, that consists of 1, 0, 1, 2, 3, 4, and 5. And let's look at, I want to look at H. So let's let H equal the set consisting of 0 and 3, and let's let K be the set consisting of 0, 1, and 2. Remember, the operation in Z6 is addition mod 6. And so let's first look at H. So I want to consider each of these separately. So we first consider H. Now, it should be clear that H is closed under the operation, but there's three things to check. So we'll have 0. I don't really want to use this. Well, I'll use the symbol. So remember, plus the operation in Z6 is addition mod 6. So I'm using a plus sub 6. If I do that, we get 0. If we do 0 plus 3, we get 3. If we do 3 plus 3, we get 6, which is 0. And I guess officially we need to check this in the reverse also. So 3 plus 0 equals 3. So these four things verify that H is closed under addition. H is closed under addition mod 6. Okay, so now we've got a binary operation on H. Now we need to check the three axioms. Associativity, well, we already know that addition mod 6 is associative when working with elements of Z6. So that means it's automatically associative when we work with just this restricted set right here, right? If it holds for all of them, then it certainly holds when we only deal with 0 and 3. So the way we say that is that associativity is inherited from Z6. And that's actually true in general. Anytime if you have a subset of some group, the operation will be associative automatically on that restricted subset, right? Just because it's associative in the big group. Let's see, what else do we need? Well, we need an identity. Well, so 0 is an element of H, and that's the identity. And then the last thing, inverses. So the inverse, well, let's say 0 is the inverse of 0, and 3 is the inverse of 3. So each element there is its own inverse. Conclusion then, conclusion is that H is a subgroup of Z6. So now let's look at K. So now consider K. And I mean, the first thing to notice, so note that 1 plus 2 is equal to 3, which is not an element of K. And so K is not closed. Right, so what does that tell us then? It can't be a subgroup because it's not even closed under the operation. Right, so therefore, K is not a subgroup of Z6. Okay, what we're going to do next is we're going to get a theorem that gives us a streamlined way to decide whether a particular subset of a group is a subgroup. Right, so this is theorem 5.1, which I usually refer to as the subgroup test. And before I actually give the statement, let's just remember what we were doing a second ago. We were talking about or checking to see whether H was a subgroup of Z6. And what we did, we went through and we said, okay, well, let's check closure. So we had to check closure. And then we noticed that associativity is inherited, which means that there was nothing to check there. And then we had to check identity and inverses, right? And so this theorem is in particular going to allow us to avoid even thinking about associativity. We will never, when we're talking about subgroups, have to worry about associativity. It's inherited. So the theorem goes like this. Let's let H, let's say this, yeah. So let's let H be a non-empty subset of the group G. Then G is, not G, then H is a subgroup of G if and only if two properties hold. So property 1, S times T is an element of H for all little s and t in H. And property 2, S inverse is an element of H for all little s in capital H. So to verify that H is a subgroup, right? We've got some subset. To show that it's a subgroup, we need three things to happen. Number one, H has to be non-empty, right? That'll usually be obvious, but it is something that's needed, and we'll see in the proof that we need that. Right? So H needs to be non-empty, and then it needs to be closed under multiplication and closed under inverses. So non-empty, closed under multiplication, closed under inverses. Okay, now for the proof, this is an if and only if, so we need to go in two directions. So in the forward direction, if if H is a subgroup, right? So if H is a subgroup of G, then H is a group, right? That's the definition. And so 1 and 2 automatically follow, right? It's got to be closed because that's part of being a group, and every element has to have an inverse, right? Because that's also part of being a group. So, one. Well, so, we can I guess put it in the details. And so, let's see. Then H is a group. That follows that H is closed. That takes care of part 1, and every element of H has an inverse, and so we're done. That takes care of part 2. Right, so the forward direction is there's nothing really to show here. If it's a group, of course it satisfies 1 and 2. Now in the reverse direction, we're going to assume that 1 and 2 hold, and we need to show that the group axioms hold for H. So first of all, so 1 shows us, or tells us, that H is closed, right? And so we have a binary operation, or so actually, like I should say, the operation on G is a binary operation on H. That's a long-winded way of saying closed. So part 1 tells that it's closed. And now we need to check the other axioms. Of course, now associativity, since it's associative on G, it's associative on H. So since this operation is associative in G, this property is inherited by H. So that takes care of axiom 1. We have associativity in H. So we've got an associative binary operation now. We need an identity. Let's see. Oh, right. So let's let little s be an element of H by property 2. S inverse is an element of H. So it follows that let's write it this way, that E, which is S times S inverse, is an element of H by property 1. Let me get out of the way. And so what just happened here, take some element of H, and my goal was to show that we've got an identity in H. So if we take, I just chose a random element, doesn't matter who I chose. By property 2, we're guaranteed that the inverse is in H. And then I multiply those two elements together, S times S inverse, which we know gives us the identity. And now, how do I know that the identity is in H? Well, by property 1, anytime we multiply two elements of H together, we get an element of H. In particular, if I multiply S times S inverse, I get to conclude that the identity is in H. Right? So that takes care of axiom 2 for groups. And then, of course, property 3 tells us that we've got our inverse. Sorry, not property 3. Property 2 tells us that we have all our inverses. So property 2 tells us, I should say property 2. So just starting a sentence like that. So property 2 tells us that the inverse axiom holds for H. So it's a fairly straightforward proof. The only trick was right here in showing that we had identities. In fact, I mean, what's going on here, right? So let's kind of recap what happened here. We assume that it's closed under multiplication, right? So we've got this binary operation on H. Associativity we get for free. Inverses we get for free. So the only thing we need to do was verify that we have the identity sitting inside H. And now, where I should ask you should ask yourself this: where did I use non-emptiness? It's right there. The fact that H was non-empty allowed me to say the sentence, let S be an element of H. As soon as I had at least one element in H, I know that the inverse is in H. Multiply it, and that gives me the identity in H. So it's kind of a fun proof, right? And that's called the subgroup test. So let's do some examples now. So let's see. First example. Let's let little n be any natural number, and define the following set, n times z. This is going to be the set of all things of the form nx, where x runs through all of z. So it's all multiples of n, right? All integer multiples of n. And what we want to do is show that nz is a subgroup of z. Okay, so I'm going to apply the subgroup test. And so here we go. So I guess I'll write proof here. Clearly, nz is non-empty. Right? In fact, there's an infinite number of elements in nz, all possible multiples of n. Okay, what's next? Okay, so now I need to show closed under multiplication. So let's pick, how about little a and little b in nz? Then, okay, what does that mean? It means that A is some multiple of n, so let's say A equals nx. Same for B. B equals n times y for some x and y in z. So it follows that, so let's see now. I need to multiply, and need to be a little bit careful here. I shouldn't have even really said the word multiply, but axiom 1 of the subgroup test says you need to show that it's closed under multiplication, and what that means is closed under the operation. In this case, we're working in Z. The operation is addition, so I want to look at A plus B. That's equal to nx plus ny, which is n times x plus y. That's definitely an element of nz. Also, minus x, which equals minus nx, which equals n times minus x, is an element of nz. So I showed that it's closed under the operation. I showed that every element has an inverse. So by the subgroup test, NZ is a subgroup of Z. Okay, next example. So let's let H equal the set consisting of the following integers, 0, 4, 8, and 12. And what we want to do is we want to show that H is a subgroup of, I think I want to do Z16. So once again, it's obvious. I just wrote H. It's got some elements, which means that it's non-empty. So clearly, H is non-empty. Now I need to show that it's closed under multiplication. In this case, what do we mean by multiplication? The operation in Z16 is addition mod 16. Now, officially, we got to brute force this. We need to show that anytime if I add any pair of elements, mod 16, I get something back in the set. So I'm going to actually grind through the entire process. All right, so let's see how many different combinations we have to do. So now observe. So I'm going to do 0 plus 0. That's an H. 0 plus 4. That's 4, which is an H. All right, officially it's a little sub 16. I don't want to have to write a sub 16 every time. So the operation is addition mod 16, but I'm just going to use a plus symbol there. 0 plus 8, that's 8, is an H. 0 plus 12 equals 12, which is an H. Now, 4 plus 0 equals 4, which is an H. 4 plus 4 equals 8, which is an H. 4 plus 8 equals 0, which is an H. And 4 plus 12, oh, no, it's not, it's equal to 12. Sorry. And then 4 plus 12 equals 0, which is an H. Halfway there. 8 plus 0 equals 8, which is an H. 8 plus 4 equals 12, which is an H. 8 plus 8 equals 0, which is an H. And 8 plus, 12 equals 4, which is an H. And now one more to do. I know this is tedious, but I'm just going to be complete in this case since it's only the second example of using the subgroup test. In general, there are times when you're just going to kind of wave your hands and say, look, if you take any two elements in here, add them together, mod 16, you're going to get something in there. All right, that's the general idea. But for now, I'm just going to brute force it. So now 12 plus 0 equals 12, which is an H. 12 plus 4 equals 0, which is an H. 12 plus 8 equals 4, which is an H. And 12 plus 12 equals 8, which is in H. Conclusion. H is closed under the operation. And I know some of you might be saying, why aren't you writing a plus 16? Well, at some point, we're just going to realize that we don't need to write the plus 16 as long as we remember when you're in Z16, right, the operation is addition mod 16. Now, okay, so that checks closure. That's the first part, and then the second part. So now, note that, let's see, the inverse of 0 is 0. The inverse of 4 equals 12. The inverse of 8 is 8, and the inverse of 12 is 4. Notice that I'm writing, since we're doing addition, which is a commutative operation, I'm using additive notation all the way through rather than multiplicative. Okay, so now by the subgroup test, by the subgroup test, H is a subgroup of Z16. Okay, let's see, next example. So just a reminder, so recall, GLNR, remember, that is the group of invertible n by n matrices under the operation of multiplication, and it is a group. All right, so this is n by n invertible matrices. Entries in R, operation is matrix multiplication, right? It turns out to be a group. Now, I want to define, so let's let, well, let's just call it S. So S is equal to the set of all elements of GLNR such that the determinant of A is equal to 1. Right? So here's a subset of GLNR, and what we'd like to do is actually we're going to show that it's a subgroup of GLNR. So first note that the identity matrix definitely has determinant 1, and so it's an element of S. So now, let's say A and B be elements of capital S. Right? So that means that they are invertible n by n matrices whose determinant is equal to 1. So then, let's look at the determinant of A times B. The determinant has a nice property that's equal to the determinant of A times the determinant of B. And so that's going to be 1 times 1, which equals 1. And so, AB is an element of S. A times B is an n by n invertible matrix. Its determinant is equal to 1, which means that it lands back inside S. Also, the determinant of A inverse is equal to 1 over the determinant of A. There's another property of determinants that we have, which is equal to 1 over 1, which equals 1. And so, A inverse is an element of S. So what have we done? We've got a non-empty subset of GLNR. It's closed under multiplication and inverses by the subgroup test. We know that S is a subgroup of GLNR. So by the subgroup test, S is a subgroup of GLNR. And this actually has a special notation So in the future, we're gonna come back and see this group, every once in a while. So this group S, which is a subgroup of GLNR, so the notation is S is actually written as SLNR. GLNR, that's the general linear group. SLNR, that's the special linear group. So S stands for special. Let's do, we'll do one more example, I think. Let me see how much time we've done here. Yeah, we'll do at least, we'll do, this is sort of a lengthier example, but this is important. So this may be one of the key examples that we want to look at for this section. So in fact, I don't even want to call it an example. Let's just call this a discussion here. So let's let G be a group. And I want to choose an element. So let's say, and let little g be an element of capital G. Now, I want to think about a certain set. So let's consider the set which has special notation angle brackets around little g. And who this is, it's the set of all possible powers of g. So it's g to the n, where n runs through all elements of z. So let's just notice a few things here. So first note that g, that's g to the 1, which is definitely an element of angle bracket g. So little g itself lives in this set. So what does that mean? That means it's not empty. Let's see. Now I want to show that it's a subgroup of capital G, right? I want to show that angle bracket G is a subgroup of capital G. And so to do so, I know that it's not empty. Now I need to show that it's closed under multiplication and inverses. So let's pick, how about x and y in angle bracket little g. So then what do those elements look like? So then x is going to be, say, g to the m, and y is going to be g to the n for some integers m and n. Now, if I look at x times y, notice now I'm using multiplicative notation because we're just in an arbitrary group G. We don't know that there's no requirement that it's abelian, so I'm going to use multiplicative notation. So now x times y, that's g to the m times g to the n, which is g to the m plus n, which means that x times y is a power of g, which means that it lives in angle bracket G. And x inverse, that's equal to g raised to the minus m. That's another power of g, which means it lives in angle bracket G also. So, by the subgroup test, all right, we've got a non-empty set that's closed under multiplication and under inverses. By the subgroup test, angle bracket G is a subgroup of capital G. And this has a special name. So angle bracket G is called the cyclic subgroup of capital G generated by little g. let's say a few more words about this group, and this is going to be a special group. We'll spend a lot of time studying cyclic subgroups. Let's just say a few more words about it. So suppose, still working within the same discussion, so we've got our group G. So suppose H is some subgroup of G, and that little g is an element of capital H. Now, since H is closed, that means, so remember, anytime that if you multiply elements from H, it lives in H. So that would mean then that all possible powers of G have to live in H. So since H is closed, G to the n is an element of H for all n in Z. So what does that tell us then? So it follows that the subgroup generated by G is contained in H. Here, I'm just using a subset symbol. That's all I really care about. It turns out it's actually a subgroup of H, but that's beside the point at the moment. What that tells us then, every time if we have a subgroup of G that contains little g, then that subgroup must contain the entire cyclic subgroup generated by little g. So the picture is something like this, right? I've got capital G. I've got some subgroup, and then I have a little g sitting inside H. So if little g is sitting inside H, then the entire subgroup generated by little g has to be inside H also. In other words, and this is the terminology that this allows us to conclude, or this terminology this conclusion leads to this terminology. I don't know what I just said there. I'm just going to write down the sentence. So this can be interpreted this way. This means that angle bracket G, the cyclic subgroup generated by G, is the smallest subgroup of capital G that contains little g. Right? Every subgroup that contains little g has to contain the subgroup generated by G. Right? So this picture is somehow captures what's going on here. Every time we have H containing little g, it contains the entire subgroup. I guess that's a good place to stop for today. We will pick up and talk more about cyclic subgroups on the next time.